Early software development and verification methodology using hybrid emulation platform. Abstract. This paper proposes another hybrid emulation platform for software development and verification of a mobile AP application processor designed at the early stage of RTL, register transfer level design. The proposed platform adopted the core emulation of ESL, the electronic system level simulation and hardware emulation. Most of the IPs are allocated to the hardware emulator side to help start software development with RTL design. CPU memories and peripherals, which are used frequently for the Android platform boot up, are allocated to the ESL virtual platform side, which maximizes runtime performance of software. Proposed transactors for IPs for external communications such as memory storage, camera module and display modules operate in the same way as real hardware devices work, and proposed shadow memory reduced the emulation time by supporting backdoor and front-door transactions with a cache scheme. Also, automation of platform build process minimizes time overhead of building a hybrid emulation platform. Application results show that building an Android platform can be completed within 45 minutes in proposed hybrid emulation platform, and show that a hybrid platform can be successfully developed before a silicon-based development board is ready. Finally, the proposed platform also helps enhance the quality of software by saving more time for design and validation for software developers. Introduction. As the competition in smart device industry is identified, importance of the TAT, turnaround time reduction of a mobile AP development has been greatly increased. To shorten overall the TAT of the mobile AP development, it's crucial to shorten software development and verification TAT. However, software development process usually starts after a development board is delivered to software engineers, though there is just a fully functional RTL design a few months earlier than the board delivery. This is because full chip level simulations cannot provide enough execution speed required at software development stage. There have been many studies to accelerate simulation speed by adopting the emulation technology, but the approaches are not sufficient for software development. Therefore, this paper proposes a new methodology to provide sufficient execution speed to develop and validate software at RTL design stage by adopting hybrid platform design methodology, which uses hardware emulation with virtual platform technology. 2. Related research. In developing a mobile AP SoC, software such as device drivers, Linux kernel, and Android platform use speed developed on its real hardware platform. The hardware is designed with an RTL designed with after definition of a specification. Verified RTL designs are fed to the implementation stage for making silicon chip. This chapter introduced software development and verification environment at each design stage of a hardware design from specification to silicon. 2-1. Specifying the using of a hardware platform. In general, the first step of the mobile app development is specification definition. In order to define the specification, estimation of power consumption or performance of a target mobile AP is used. ESL environments are used to measure power and performance values of a target mobile AP. In this case, the ESL environment is a system-based system, a system C-based system, and has advantages in easy adjustment of abstraction level of the design. The concept of the ESL is defined 1 and described as below, which is quad of 2. The definition of ESL system, electronic system level, is an emerging electronic design methodology which focuses on the higher abstraction level concept first and foremost. ESL is now an established approach at most of the world leading SoC system on chip design companies and is being used to increasing in design system design. From its genesis as an algorithm modeling methodology with no links to implementation, ESL is evolving into a set of complementary methodologies that enable embedded software, embedded system design, verification, and debugging through to the hardware and software implementation of a custom SoC, system on FPGA, system on board, and an entire multi-board system. So the ESL can be accomplished through the use of System C as an abstraction modeling language. Therefore, in ESL environment, a hardware platform can be built easily by adopting high abstraction level models in early design stage. ESL environment is useful in software development and verification due to its rapid simulation speed. The hardware models which are used in an ESL environment can have various abstraction levels with different level of cycle accuracy. As shown in Figure 1, there are 4 kinds of abstraction level according to cycle accuracies. CA, cycle accurate models have highest accuracy same as RTL design. AT, approximately time, the model have 80 to 90% accuracy level, and the LT, loosely timed models have 60 to 80 accuracy level. FA, function accuracy models guarantee 100% function accuracy but do not have timing information. The higher cycle accuracy of the hardware models can provide a higher timing accuracy in overall simulation, but it results in a more slow simulation. In slower simulation speed. However, it is in inverse proportion to simulation speed. If only FA models are used in the hardware platform, a simulation speed can be from a few dozen megahertz to several hundred megahertz. On the other hand, if the CA models are used in hardware platform, the simulation speed can be from a few dozen kilohertz to several hundred kilohertz. At the specification stage, AT or LT models are more often used than the CA models because they can be made more quickly and easily than CA models. Furthermore, TLM, transaction level models are used extensively in order to reduce overhead for modeling because there is no need to implement transaction protocols in detail. Therefore, TLM LT and LT models are used widely in ESL. Figure 1 is the ESL model, cycle accuracy and simulation performance. The 2-2, RTL design stage of the hardware platform. After specification of mobile IP is defined, RTL design for each IP module and the module start at RTL simulation is used for RTL verification. These RTL netllists are used for gate-level synthesis and hardware implementation. Therefore, RTL netllists are initial real design. RTL simulation is used for accurate function and timing verification. However, simulation speed is inversely proportional to the design scale. As the design size grows, the simulation speed reduces exponentially. In case of several hundred million gate scale, the simulation speed can be dropped to a few dozen kilohertz. This simulation speed is 10 to the 6th power times slower than a silicon speed. Therefore, the software which runs during the 1 second, one silicon can consume the 10 power to 6 seconds, 11.6 days for simulation. It is almost impossible to force simulation to be used to software development and verification with a long time duration. Recently, emulation technology used to accelerate speed of the RTL simulation in many SoC design companies. It's known that the speed of emulation is 1,000 times faster than that of simulation. The emulation speed can be from the several hundred kilohertz to several megahertz. The emulation speed is 10 to 3 power times slower than the silicon hardware. It can be applied to the software development and verification. Software which runs during 1 second on silicon can consume the 1 to 3 power second 16.27 minutes for running. The emulation can be adapted to develop hardware support as a device driver, which are relatively simple. However, it is not faster enough to be used for development of Linux kernel and Android platform, which are relatively large scale of the complex, because it can be more than 10 hours to reboot Android using emulation platform. 2-3 Advanced RTL simulation environment. Software development and verification need to be started at the earlier stage of RTL design as possible to secure enough time to develop. In order to start software development at the early stage of the RTL design, and RTL simulation environment can be used for development platform. According to the previous research for an acceleration of the RTL simulation, it's shown the FPGA-based test board has about 10 MHz simulation speed. However, due to a limitation of FPGA scale, it's difficult to port full mobile AP to FPGA test board. Platform build can increased due to the RTL modification to fit the FPGA board, or due to the fine-tuning for synthesis. In order to the above the limitation of FPGA test board and to the secure fastest RTL simulation environment, ESR simulation and co-emulation technology were proposed in 8. This method uses systems based in the TLM model instead of the RTLs for some IPs. A simulation speed is bounded by the emulation speed when IPs allocated to the emulator are accessed. On the other hand, simulation speed is bounded by the simulation speed of TLM models. When a ESL co-simulation methodology is applied, the additional time is required for IP modeling and virtual platform build. However, total simulation time can be reduced by a trade-off between the model's period and ESL performance. In the previous research, ESL the co-emulation methodology was used for GPU verification. The GPU for which a verification was required was allocated to an emulation platform and other IPs such as CPU and memory. Subsystem prefers for boot sequences are allocated to an ESL simulator. In the search, OS boot up was completed very quickly, and because the CPU and the memory subsystems were allocated to the ESL side. Software for OS booting and predefined hardware platform, which has been already applied to the ESL environment, was used. Since the research only focused on the functional verification of GPU device driver, and predefined hardware platform and the OS booting software were suitable. So as a result, the OS boot software used in a mechanism cannot be applied to the real mobile AP device. Furthermore, another existing research used the ESL co-emulation methodology to develop and verify software. They focused on the CPU and core operation of they used the VIP verification IP for external devices. Full system of mobile AP was not a focus in the search, and it was difficult to adopt the co-emulation platform for software development due to a limitation of VIP. VIP can operate with only predefined IP configuration if all kinds of IP configuration are defined as the same as a real device. There are no problems to be used for OS boot up, so the VIPs, which are models on or SFR, special functional register, and each function should be called transactors. Therefore, the platform has a limitation in developing a full Android platform with their co-emulation platform. 3. Hybrid emulation platform. As shown in the previous chapter, rapid simulation environment should be secure to start the software development and verification at RTL stage. At the RTL design stage, ESL RTL co-emulation methodology should be applied to guarantee enough runtime performance for software development. Furthermore, the methodology should support the same environment as that of a real silicon mobile AP, and the overhead to the setup the platform should be minimized. Therefore, this paper proposes a hybrid emulation platform which enables software development and verification at the early RTL design stage. The proposed hybrid emulation platform can reduce software development time also. It uses a co-emulation methodology. CPU and memory components are allocated to the ESL virtual platform side with the TLM LT models because they issue a lot of transactions during boot up time of the Android platform. Other IPs are allocated to the hardware emulator side. Furthermore, the virtual external storage and display modems and camera models are connected to the 5 models through the transactor which were developed in this research. The proposed hardware emulation platform can provide the same environment of a silicon-based developed board and enables the development and verification of the software related to external devices. By following the proposed automatic platform generation flow, timing of ready to build a virtual platform and the hardware emulation platform can be minimized. This chapter shows the proposed algorithms. 3-1 Architecture of a hybrid emulation platform. The proposed hybrid emulation platform is composed of a virtual platform and the emulation platform. A virtual platform is an ESL hardware platform based on TLM LT models. CPU, memories, and external devices are allocated to a virtual platform due to a lot of memory transactions. During Android platform boot-up sequences, CPU, memories, and external storage and display modules are operated very frequently. Therefore, they should be allocated on virtual platform. Figure 2 shows an overall view of the architecture of a hybrid emulation platform in the experiment. Figure 2 Hybrid platform overviews. IPs with a high speed requirement should be allocated to virtual platform with the TLM LT models to increase the performance of hybrid emulation platform. Any IPs which is already models can be allocated to the virtual platform side. Other IPs will be allocated to the emulator side, and TLM LT models in the virtual platform are connected to IPs in the emulation platform using transactors, and these transactors are used for communication between virtual platform and the emulation platform. The transactors use signal hooking and a forcing method to transfer data to other domain. And this in the viewpoint of emulator, virtual platform looked to be one of RTL modules. On the other hand, the emulation platform looks to be one of TLM LT models and the viewpoint of a virtual platform. 3-2 Transactors on a domain conversion. As described in 3-1, adopted so-called transactors were which enable communication between virtual platform and the emulation platform. A transactor is implemented in the emulation platform does not change the original functionality of a given duty because it only performs the signal forcing and the signal hooking to transfer data between two platforms in different domains. transactor platforms protocol conversion between transaction level protocol used in the virtual platform and pin level protocol used in the emulation platform. The transactor also has an internal buffer to overcome speed gap between virtual platform and the emulation platform in the proposed hybrid emulation platform. We adopt the transactor for AMBA AC protocol interface, sideband signal and files for eMMC and UFC and display and camera. With these transactors, it was possible to provide a user interface which is identical to that of a physical mobile set, and hence it enabled software development and validation for full-chip mobile AP. Figure 3. Transactor Overview. 3-3 Timing Synchronization Framework. The proposed novel timing synchronization framework to avoid the phenomenon that the maximum system speed is limited by the relatively slow emulation platform when synchronized at every cycle. As shown in Figure 3, a cache scheme in the internal buffer of each transactor is adopted, and it helps to enhance the overall system operation speed by reducing synchronization frequency between two platforms. 3-4 Memory Shadowing. In our hybrid emulation platform, memory shadowing schemes has been adopted to improve memory access speed. When an IP such as CPU and the virtual platform requests memory access, the request must be passed throughout the main backbone in the emulator platform, and it gradually limits overall system speed at the emulation platform speed. To avoid this approach degradation, we adopted a memory shadowing scheme. Details of the scheme is described in Figure 4. This scheme is located between the virtual platform and emulation platform. It supports fast memory access from virtual platform and emulation platform also. With the proposed scheme, a huge amount of the memory access in Android boot process is performed well, and overall simulation speed enhanced drastically. Figure 4 Memory Shadowing Architecture. 3-5 Automation Flow for Hybrid Platform Build. It requires extra design work to create a virtual platform and emulation platform with the transactors build a hybrid emulation platform. Users need to set a memory map for a proper access control, and also need to set an interrupt map to the guarantee correct behavior of a GIC located in virtual platform. Moreover, CPU, memory, and clock is reset, virtual storage, and all preferred models require connection between the virtual platform and the emulation platform. These processes generally started with a pure emulation platform and incrementally refined for the emulation platform DB is applied. Users need to include APs in emulation platform by marking it as a block box when an IP is created in a virtual platform, and place the transactor to communicate IP in a virtual platform and the surrounding blocks in the emulation platform. Users need to rewrite a test bench, which include the processes described in previous sentence, and need to perform emulator porting again. In our experiment, we found building hybrid platform is a time-consuming and error-prone process. This is mainly because the traditional validation and verification methodology covered virtual platform or emulation platform, and it does not cover the crossing boundary. Therefore, we propose an automation flow to minimize manual design effort, which will also minimize the human errors as well. Automation flow include modified emulation platform, DB creation process, and virtual platform creation process. The proposed automation flow generates an emulation platform DB creation script with the transactors and IP information written in a predefined input format. Also, virtual platform creation is automating with the memory map, and the interrupt map is written in the predefined format. In our experiment, we identified we can reduce 37% of hybrid platform creation time with the proposed automation flow when compared to that of a full manual design work. though time to create a hybrid platform had 3% override when compared to that of pure emulation platform creation. It is only 10 minutes and is negligible. Okay, figure 5, automatic hybrid emulation platform generation flow. 4. Application result. And 4. Methodology validation. We apply to the hybrid platform design methodology using our core emulation framework for up-to-date flagship mobile AP. In our experiment, full SoC including preferred and storage interface along with the corresponding transactor and device models are also implemented in hybrid platform for complete device driver development and validation. Target AP consists of 2.5 billion logic gate and has 30 preferred and 7 external storage devices. Full chip mobile AP was used for validation of a hybrid emulation platform. 4-1 Platform build time. The proposed hybrid emulation platform has 2 additional steps for platform build compared to pure emulation platform. The one is the transactor integration, and the other is a virtual platform build. The transactor should be connected to a top design using RTL list. Therefore, some RTL files can be modified and recompiled. During the build of a virtual platform, IP instantiation and signal or interface connection model configuration should be performed. Therefore, timing overhead for these steps is not small. Table 1 shows the comparison result for platform build time. In case of a pure emulation platform build was completed relatively quickly because virtual platform build and transactor integration is not required. In case of a hybrid emulation platform build time increased to 63% by adding time for manual virtual platform build and transactor integration. In order to minimize this timing overhead, automatic platform generation flow was applied. By the result data, automatic platform generation flow reduced platform build time is 35% compared with the manual platform build time. In conclusion, the platform build time of the proposed platform was increased by 3% compared to the pure emulation platform build time. Table 1 is a comparison of platform build time. 4-2 Performance comparison. Device driver for all IPs and the Android platform setup were performed on the hybrid emulation platform. Finally, Android platform porting was completed on the platform before design of the development board. Table 2 shows that the comparison result for consumed time at each software step among simulation, pure emulation, and hybrid emulation platform. In case of the RTL simulation, time values were estimated using total cycle number for Android platform bootup and CPS cycle per second, and the values were used for a comparison to each low simulation speed. Otherwise, the pure emulation and hybrid emulation platform were compared using real experimental values. As shown in the table 2, initialization time of the simulation was shortest because emulate initialization and DB image transfer are not required in a simulation. However, time difference with the pure emulation and the hybrid emulation platform was within 1 minute. It may be referred to as meaningless difference based on the total consumption time. For Linux kernel boot, simulation speed has been increased by 48 times when compared to that of a pure emulation platform. Overall, Android OS boot process took less than 1 hour and can provide efficient OS and boot code validation environment for software developers. It is 14 times faster than pure emulation platform. During the Linux kernel boot-up, most of operations are done in the virtual platform. And furthermore, communication between virtual platform and emulation platform also is not much. Therefore, a high timing gain of the hybrid platform was shown. However, timing gain of Android platform boot-up is just lower than that of Linux kernel boot-up because a lot of operations such as initialization, registers reprogramming, at least the programming and real function process for each IP were done in emulation platform, and a lot of communications was done during hardware platform boot-up. The operating time for Android platform boot-up has accounted for 87% of the overall operating time. The timing gain on Android platform boot-up represents timing gain of over hybrid emulation platform. The table 2 is a performance comparison. The figure 6 shows Android's home screen as a result of Android platform boot-up and the proposed hybrid emulation platform. We were able to see the image using virtual LCD in the virtual platform. The frame data which were generated by display modules in emulation platform was saved in the frame buffer. The virtual LCD displayed the image by reading frame buffer using display file transactor. The proposed platform provides software development and environment similar to the development board. Figure 6 Android home screen as hybrid emulation platform. As shown in table 2, a dozen of debugging runs were possible when a hybrid platform is adopted, because only 7 minutes were enough for one Linux kernel booter. It did not show any significant difference with the development board. In case of Android platform booter, simulation speed was slower than the development board. However, multiple debugging runs per workday was possible with this hybrid emulation platform. We started developing and verifying hard softwares at early RTL design stage using a hybrid emulation platform. Display modules, camera modules, and mobile storages such as eMMC, UFS, and USB can be integrated to the proposed hybrid emulation platform using various transactors. Most of the devices, including in a mobile AP chip, were developed and verified using platforms as the same way of development board. 5. Conclusion. This paper proposed a hybrid hardware platform emulation platform which enables early software development and pre-silicon stage where RTL design is available. So to enable optimized software development and validation environment for mobile AP designs, transactors were designed to communicate with the off-chip device implemented in a virtual platform. Moreover, overhead access time of memory devices was minimized by placing CPU and memory subsystem in virtual platform. Application results showed 14 times faster simulation speed for Android boot-up compared to that of a pure hardware emulation system. Also, automation of a hybrid platform creation flow reduce the design time of the hybrid platform and reduce human design errors as well. By applying the hybrid emulation platform to a software development and validation process, an Android platform was successfully developed before the delivery of a development board along with the tap out of the mobile AP chipset. The hybrid platform also helped enhance quality of software by allowing the software developer to do more design and validation. for future work will be to enhance the automation flow of a hybrid platform with an IP exec-based platform integration methodology. Also, more investigation on communication override between the virtual and emulation platforms will enhance the IP modeling methodology. Okay, here is the thank you for your time. Today I read the DVCON paper, Early Software Development and Verification Methodology using Hybrid Emulation Platform. Thank you again and see you next time.